right, so we're going to work through some examples today dealing with interpreted spectra and also talking about like some complex splitting. I think that won't be too bad once we get to that particular example. And then we're going to talk about how to assign spectra, and then all of our interpretation is going to be on what we already know. So splitting patterns, chemical shifts, and integration, and things like that. So we got 4 molecules that we're going to look at are represented by these signals right here. Right, that would correspond to these 2 protons right here. Now, what do you notice about those signals? What do you think? Okay, so let me back up. The NH2 is not going to split. Okay, so what would, if this was just a regular CH2 with no chiral center next to it, what do you think the signal would look like? What should it be?
It should be 6 peaks. What?
Why,
No.
why do you say that? If this was just a regular CH2 group with no chirality next to it, how many neighbors would it have if you know that this set of protons right here is not going to split with it?
No. Okay, so it would be 4 neighboring groups, and then wouldn't it be 4 plus 1?
Where are you getting 4 from?
The kind of
hydrogen.
3. I only seeing 1. Would it be only 1?
It's only 1. It's this hydrogen right here that it's going to split with. Because if it can't split with the NH2, right? That's on this side. Are you following? And then there's a carbon on this side of that carbon, and it only has 1 proton on it. Is that clear or no?
No.
So we're looking at these hydrogens. Let me back up. The question I asked was if there was no chirality at all, right? How would these hydrogens show up in the spectrum? And we know, to add on to that information, the NH2 is not going to split, right? You can't count those as neighbors, right? So what are my neighboring atoms? It's the nitrogen, is that right? And then it's this carbon here. These are my neighboring atoms. Sorry about that. These are my neighboring atoms here, and the nitrogen right here. Is that right?
Mm-hmm.
So how many neighbors would this set of protons have if we weren't talking about it being next to a chiral center? How many neighbors would it have?
No,
Just 1.
Just 1. So the signal should be a doublet under normal circumstances. Is that right?
Mm-hmm.
Does everybody agree with that?
So you only split between carbons? You're not doing any other atom?
No, what I'm saying is that the NH2, they don't couple. Those protons don't couple. OH protons don't couple. So you don't count them. If you're looking at a set of hydrogens and it's next door to a OH or an NH2 or an SH or any hetero atom, you don't count those as neighbors because they're not going to split.
Okay.
Yeah. All right. So normally that would be a doublet. Is that right? Does anybody disagree or still not see it?
When you were looking for the neighbors for the teal hydrogen,
Mm-hmm.
why were you able to count the CH3 ones and the NH2 ones?
Oh, no, I didn't count the CH3 now. I'm only looking at the immediate neighbors.
No, when you were talking about the teal hydrogen.
Oh, the one here.
Yes.
Yeah. So this is it's on this carbon, right?
Yes.
So this carbon is next door to this carbon.
Mm-hmm.
And it's next door to this carbon with the CH2.
Oh, you okay.
I'm only looking at the immediate neighboring atoms. Are you following?
Okay. Yes.
Okay. So you'll count the CH3 and the CH2 for this proton simply because those 2 carbons that are neighboring have hydrogens on them that can split with that proton. But the NH2 That's adjacent to, let me erase some of this stuff. The NH2 here is adjacent to this carbon. Right? So you have the NH2 that's adjacent, and then you have this carbon that's adjacent. And so that's why I'm saying under normal circumstances, though that set of protons would be a doublet, because the NH2 is not gonna, for any heteroatom is 0. So you don't count those. Are we okay now?
Mm-hmm.
All right. So, but you'll notice if you look at the signal, right? If you look at the signal right here, it's not a doublet. It's actually two doublets together. Do you see that? How it's 4 lines?
Yeah.
It's not one. It's not a single doublet. So what happens? And I hope this doesn't like go through the roof, but we're gonna try it. We're gonna get it. What happens is, let's say for this proton right here, right? Since these two are non-equivalent, right? Those two are non-equivalent. E looks terrible. They're non-equivalent. Everybody agree with that. We already established that they're non-equivalent because they're next door to a chiral center, right? So they're not the same. So because those are non-equivalent, they actually split each other. So they're going to split each other. So this, for this proton, it's going to actually split with this proton, and it's going to split with this proton. So when it splits with the red proton or the pink proton that I just highlighted, what should that give you? If you're using the n+1 rule, it should give you a doublet, right? If we're talking about this side right here now, so this should give you a doublet, right? And then what happened? What do you think about when it splits with this proton right here? What should that give you? If it's only one, and we apply the n+1 rule,
Doublet.
that should also give you a doublet. Is that right? So this right here will give you a doublet, and then here you'll also get a doublet because n+1 is going to equal 2. So now let's go back to the signal. Can you see how that signal is 4 lines? Right, so this signal is 4 lines, but it's not a quartet, right? So we call this signal a, let me write it over here, a doublet of doublets, right? You only see that if you have that type of complex splitting where you have a chirality center adjacent to a set of protons. That's the only time you're going to see that, right? So it's 4 lines, but it's not a quartet, and a quartet is normally symmetrical. A quartet would normally look like this, where you have 2 outside lines and then 2 inside lines that are the same height, but you don't see that there, right? And that's only because of that chiral center.
So for those individual hydrogens, wouldn't they both have 2 neighbors? Or how does?
Yeah, you talking about the two right here that are on that, the 2 distereotopic hydrogens?
Well, when you look at them individually, when you count the opposite hydrogen and the one attached to the chiral center?
Yes, but you're going to do that separately, not together. Because you're thinking that it should be a triplet. Is that what you're trying to say?
Yeah, that's how I'm looking at it.
So you have to look at each hydrogen separately. They don't split. They don't combine. because of that chiral center. And because if you think about it, let me see if I can, let me erase some of this and I'll show you why they won't be together. So let's say if that's wedged and then this is dashed, right? This is going to see this proton differently than it sees this one.
Right.
Following? And by the same token, the proton that's over here that I have dashed, it's in a different 3D orientation. So it's going to see this differently than it sees this one. So that's why you have to do them separately.
Okay. So you're just counting that hydrogen attached to the chiral center?
One time.
Okay.
And you're not combining that hydrogen with the other hydrogen that's next door to it.
Okay.
Yeah. That's a good question. It's a great observation. So it wouldn't be a triplet. It's going to couple twice. So it'll be what we call a doublet of doublets. Any questions about that? I know that kind of, that's why I wanted to do this example first, because this is the most difficult one out of all of them. So when do you expect to see that doublet of doublet type splitting come up? What's one scenario where you see it?
When it makes the chiral center.
When you have a distereotopic protons adjacent to a chiral center. That's exactly right. So let me write that down somewhere. Excuse the silence while I'm writing. But you see a doublet of doublets, not doublets. Right, you'll see that when you have distereotopic protons. There are so many different types of complex split. I just wanted to show you this one, but there are a lot of different types of complex splitting patterns. You can have a triplet of doublets. You can have a triplet of quartets, a doublet of quartets. It just depends on the situation, and it depends on what's around the protons that you're looking at. Right. So can you see that both of these doublet of doublets correspond to these protons right here? Right, because you see you got two of them, one here and one here, and they're both integrating for one hydrogen. Yes or no?
So what is the other neighbor for the pink hydrogen?
Okay, let me zoom in and make sure I can see the right color. You know, I'm getting old. So this one right here.
Yes.
So it's going to have a neighbor here because that hydrogen, the hydrogen that's on the same carbon with it is non-equivalent to it. So it's going to split with that, and it's going to split with that turquoise.
Okay, so it goes all the way up there.
Okay. Yeah, it's not, but it seems like that. But really, these two carbons are next door to one another, right? So they were split anyway.
Okay.
Is that right?
Yes.
Because that's how we apply the N+1 rule, right? We look at the neighboring atoms and see how many hydrogens are on each one.
Okay.
So they're gonna split anyway because they're adjacent. I just drew the arrow around like that, but it's not. The distance is still, they're still next door to one another.
So we would do nothing with the green H's?
No, the NH2, OH, SH, any type of heteroatom type protons, they don't split with any hydrogens that are adjacent to them. So I'm gonna write that right here. Right, so you don't do anything with those. You don't count them, even though they are neighbors technically. You don't count them when you do in your when you're applying the N+1 rule.
So technically, they wouldn't have neighbors either, though, right?
What do you mean, the NH2?
Yeah, like the hydrogen on the nitrogen.
Yeah.
They wouldn't.
Well, they do, right, on this carbon that's adjacent, but you don't count them because they don't see each other. Okay. Splitting and multiplicity happens when neighboring protons experience the magnetic field of the protons adjacent to them. But there's for some reason the nitrogen and oxygen, those protons that are on those atoms, they don't get to experience that magnetic field, and so they don't split.
Okay.
Yeah. And I have a video about this complex splitting. I'm gonna send it to y'all today. So just to reinforce what we're talking about right now. All right. Any other questions? I know this was a tough example, but I wanted to get it out of the way. So now we'll be on a downward plateau or a downward a descent. Yeah. I'm having class. I know. We're gonna get it straight. All right. Okay. Say that again. All right. So we're good on this example. Let's go to the next one. All right. So here, how many signals do we have in this example?
5.
5 signals. All right. So we know it's not this one, right? What else can we rule out? Can we rule this one out?
Yes.
Yeah, because that should give you 1, 2, 3, 4, 5, 6. If the OH shows up, 7 signals. Is that right?
Mm-hmm.
So we can rule that out. What can we rule this one out? Yeah, because we already solved that spectrum. So now we're left with these 2 molecules here, right? And we got 1, 2, 3, 4, 5 signals here, and then 1, 2, 3, 4, 5 signals here. The difference here, again, is that you don't see these vanillic protons, right? These hydrogens right here will show up somewhere between 4 and 6, and you don't see that in this spectrum. Are you following that? Like the chemical shift for these should be between 4 and 6 in ppm.